Thank you, everybody, for joining for our last session of Discrete Optimization Talks for this season. Stay tuned for more information about next season. Today, we start with Silvia Di Gregorio. She is Maître de Conférence. I'm going to butcher that. Master of Conferences, I guess, is the direct translation at the Sorbonne,
kind of a
Paris. Yeah. Well, anyway, a professor in at the Sorbonne Paris Nord University and at the Northern Paris Computer Science Lab (LIPN), where she is part of the Algorithms and Combinatorial Optimization group. Prior to this, she obtained her PhD at the University of Wisconsin-Madison and then worked as a postdoc at TU Dresden. Silvia, please, the floor is yours. For those of you in the audience, I'll write this in the chat. Feel free to ask clarifying questions during the talk. Most likely, we will save more of the technical questions for the breakout rooms that will happen after our second dot.
Okay. So first of all, I would like to thank Alex and Elias for inviting me and all of you for coming. So today I will be talking about a recent project that I did with Alberto Del Pia at UW-Madison and Florent Capelli, who is in France as well, but in London, a little closer to this. And the goal of this project was basically to see if we can leverage some known results from a different field of computer science, which is knowledge compilation, and I will introduce you to it in a little bit, in order to understand something more about binary polynomial optimization. So first of all, what do I mean by binary polynomial optimization? And I would refer to it with BPO sometimes. So this is a problem that is very simple to state, because in fact, as input, we only have a polynomial function, and we want to maximize it under the only constraint that the variables must be binary. So in order to write it down more formally, I would use two sets, V and E, where V is a ground set of cardinality n, so basically the number of variables that you have in your polynomial. And E is instead a family of subsets of V, which basically encodes the monomials. So once you have these two sets, you can write the problem as follows, where all the coefficients of the polynomial are in this vector, okay? And one way to derive some results of tractability is to take advantage of the structure of the polynomial. And in order to do it, we're going to use a hypergraph. So this is an example of a hypergraph. And in general, they're just a generalization of graphs where edges can now connect more than just two nodes. So for example, here E3 connects 4 nodes at the same time. And the relationship with the polynomial is the following. So every variable of the polynomial is represented by a node, and every monomial is represented by an edge. Now, this problem is very general, and therefore several applications can be modeled through it by, like, they go from the more classical ones, they know R and combinatorial optimization, but there are also some more curious ones, like in image restoration, in computer vision, or even in theoretical physics. Now, not very surprisingly, this problem is NP-hard, as even when you have a quadratic function, it is. But nevertheless, several approaches have been proposed, like, for example, reducing it to having a quadratic function and exploiting all the rich literature on it, or simply writing it down as an integral linear program. So, for example, several linearization schemes can be used, but the simplest one would be adding one variable for each monomial, and then putting the definition that this variable must be equal to the product in the constraints and relaxing them. So just a quick overview about which are the known instances of BPO that can be solved in polynomial time, okay? So all of them except one, so the first one, are related to the structure of the hypergraph. So this is why the first one is a bit on the side, which is simply when your polynomial is supramodular. So now let's go to the other one. So the first one has to do with the treewidth of the hypergraph. So basically, here we want to use the common concept of treewidth in graphs for hypergraph. So the idea is the following. You have your hypergraph that represents your instance. And starting from it, you construct a graph, in this case, the primal graph, and compute the treewidth of that one. If the treewidth of this thing that is simply obtained by replacing every edge with a click is fixed, then it means that you can solve in polynomial time also the original problem. Now, the other two cases instead deal directly with the hypergraph. And the next one is when H is beta cyclic. So without being tedious with all the definition, suffices to say that there are several definitions of acyclicity in hypergraphs. And beta cyclicity is basically the most general one that is still interesting and non-trivial. And finally, instead, we can also do something when we have some cycles, granted that the structure of the whole hypergraph is something like that. So basically, the goal of this project is to unify all these results connected to the structure of the hypergraph and extend them. So by unifying, I mean the following. All these cases have basically been obtained by dedicated algorithms. So each of these cases is a different algorithm. So instead, we would like to provide a unique framework that deals with all of them at the same time. And as well, this framework will be able to handle some extensions of BPO. So now I will develop the theory for BPO because it's a little bit simpler, but then at the end, I will show you which extensions of it we can also handle. Now, as I mentioned, we want to use a different field of computer science to look at BPO. So, and the main tool of this field is Boolean functions. So first, I will just define what we mean by that. So let's say that we have a finite set of variables x, okay? And we say that f is a Boolean function on this variable if f is any subset of assignments. So basically, to each variable, we can assign a 0 or 1, so a Boolean value. And any subset of those can be a Boolean function. And we say that a specific assignment tau is satisfying f if and only if tau is in this subset here that was picked at the beginning. So this machinery is already enough to represent the structure of our polynomial from a different point of view in the following way. So this is the structure of the polynomial, okay, of our objective function, where we, for the moment, don't care about the specific coefficients, so to maximize it. Okay? We only want to model the structure and how the variables interact with each other. And one way to do it is the following. So here we introduce a finite number of logical conditions, where basically we introduce one new variable for each monomial, ye, as if you would do in the simple integer linear program that I mentioned before. And on this new variable, you introduce the logical condition that this must be true if and only if all the variables in that monomial are true as well. So basically, we introduce one clause or one logical condition that represents the structure of the specific monomial. And then we ask that all these logical conditions are true at the same time for all the monomials. So basically, the f here really represents how the monomials interact with each other. Now, however, our goal as optimization people is actually to optimize the polynomial, so find the actual optimal value and the optimal solution. So we need to introduce this notion of coefficients and maximization in the Boolean function. And we can do it with these weight functions that are defined not only on the variable x, but also on the specific value of the assignments that they will get. Meaning that therefore you can define different weights, whether a variable is set to false or to true. Okay? But once you have this weight function defined for the assignment, then you can define the Boolean maximization problem as follows, which is just the evaluation of a weighted Boolean function. And we define it for our purposes exactly like that, because it works for us like this, but you can also define it in different ways. But we wanted to compute the maximum of all the assignments that satisfy the function f that represents our polynomial of the sum of all the weights. Okay? So we define f as I explained before with these clauses. And what is missing is how we define the weights. So here, in order to include the information of the coefficients, we just set the weight of the variables of the monomial when they have value 1 to PE and 0 all the other times. Okay? So on a very simple example, let's look at here how it would work. So here we have an example with the 3 variables and 3 monomials. Okay. Very easy, and we can encode it like that. So we would introduce one new variable for each monomial. So let's look at the first one. We want y1 to be true if and only if this conjunction of the three variables corresponding here in the monomial are set to 1. So they're true as well. And same thing for the other monomial, okay? And here we ask that all of them are true at the same time to represent the structure. And the weights are defined like this, and all the other weights are 0. Now, even by inspection, we can see that indeed the optimal value of our problem is exactly the same as the value of this weighted Boolean function. In fact, here we can see that since we're maximizing, we want x1 to be 1 in order to get this reward. But we would like to avoid incurring into this penalty. So we would set x3 to 0. x2, we don't really care. But so this is the optimal value, and this is the optimal solution. And we can see that also on the other side, in this machinery, we get a relating of the solution, okay? A relating assignment, because we can set x1 to 1, the other x is to 0, and we compute the value of the y correspondingly. And indeed, the value of the weighted Boolean function is the same. So we show, and the proof is pretty easy, this one, that this holds for all the polynomials, not just in this small example. And so we actually get that solving our BPO is exactly the same as evaluating this weighted Boolean function whenever f is defined exactly by representing the polynomial, and we define the weights in the manner that works out. So this is to say that we can actually indeed use all the existing toolbox for the Boolean maximization problem to address our problem. And there are quite a lot of theorems that we can use, so theoretically, but also there are some practical tools that I will describe at the end. So as I mentioned, the main tool that we're going to use are Boolean functions, okay? And the first thing, so Boolean functions are a subset of assignments, okay? But just defined like that, they're not very easy to use as just a subset of assignments. And so we need to find a smart way to represent them so that we can use them in the algorithm. This is an example of one way in which you can represent one. So here we only have three variables, x, y, and z. And this is saying that if x is false, then it's automatically satisfied. But if x is true, then we also must have that y and z are true as well, because otherwise this would be false. Now, this is already one way to represent it, but not the most convenient. So let's see if there's something else that we can do. So one easy way would be truth tables, or at least easy in the sense more intuitive. And in truth tables, what you have is simply like you have the first line where you list all your variables, and then you just enumerate all these satisfying assignments of f. Okay, so here indeed, what you have is that if x is false, then you have all the possible assignments of y and z, right? Because we don't care about them. But as soon as x is true, then y and z do not have any freedom anymore, and they both set to 1, at least in this example. So truth tables have the advantage that they're explicit, right? And very easy to manipulate, because I think even if you have the weights on the assignment, then it's immediate to compute the weight of all these assignments, and then you pick the maximum, right? But they're not compact. So it might take you, so the size of a truth table might explode. So it's not really what we would like. Okay? So another option would be conjunctive normal forms. So these are very compact, and they're basically the ends of a bunch of clauses, or you can think of them as chunks. And each of these pieces can only contain ors of variables or their negations. So basically, they're conjunctions of disjunctions of literals. And this, for example, is one CNF that represents exactly this Boolean function here. It's one line, so you can see it's very simple, and you can use CNF to encode very compactly and in a very succinct form many problems, including SAT. But they're so compact and succinct that many of the problems, if you only use a CNF, they're intractable, okay? Unless you have some additional structure. And this is the case also for us, unfortunately, so for the Boolean maximization problem, so for computing this W of f. One way in which you can use CNF is if they have some special structure. And here again, structure can be represented, like for BPO, with hypergraph. So, and the definition of hypergraph is the same as for BPO, basically. So there is one node for each variable, like here. And here, however, you totally do not care if a variable is negated or not. It will be just represented by the same exact node. Okay? And then you introduce one edge for each clause. So here, in this case, we get a graph because each clause only has two variables, two literal sections. But yeah, if you have more, you will get bigger edges and therefore a proper height. So I hope to convince you that representing Boolean functions is not that trivial. And in fact, the whole field of knowledge compilation revolves around this question. And the goal is basically to find some different representations of these functions that basically bridge between allowing tractability of the problem, but also not having like something that is used like a truth table. So you bridge between compactness and tractability. So for our purposes, one representation is the one that we'll work out, is the one of OBDDs. So I will not go into definition, but these are the ordered binary directed decision diagrams. And for those of you who haven't heard of them, at the end of the day, they're a very special type of directed acyclic graph, okay, with a root. And the one important theorem in knowledge compilation is that if your Boolean function can be represented by one of these acyclic graph, then you can compute the weighted Boolean function that we're interested in polynomial time in the size of this graph. So basically in the number of edges since it's acyclic. So now the real goal is basically understanding when and how we can represent our Boolean functions with an OBBB that doesn't blow up in size. Okay? And there are a few interesting theorems about CNF that, surprisingly or not, basically work out exactly under the same assumptions that we had for tractability of BPO, or slightly more general. So remember, we had one assumption on treewidth for BPO, and here as well, different type of treewidth. So here what we have is that if your CNF is represented by a hypergraph with fixed incidence treewidth, then you can actually construct such a small OBDD on which then on top you can compute WF. So just to explain a little bit the difference between incidence and primal treewidth. Here again, you want to compute the treewidth of a related graph. Okay, so you start from your hypergraph, and what you do is you construct the incidence graph now, which is a bipartite graph, where you have on top the vertices that represent the nodes of your original hypergraph, and on the other side, instead, you have nodes that represent the edges. And you connect them if and only if the node that you're looking at was in the specific edge. So for example, here, this node was only in this edge, and so it's connected to only one node on the other side. Okay, but for example, this one belongs to all the three edges, and so it's connected to one. Now, incidence treewidth is a bit more general than primal. So basically, one can show that if a hypergraph has found a fixed primal treewidth, then it will also have fixed incidence treewidth, but not the other way around. And the second case in which you can actually construct a small enough OBDD starting from CNF is precisely when the hypergraph is beta cyclic, exactly like for our BPO. So this started to make us think, and we showed that we can recover exactly all the known tractability results of BPO connected to the structure of the hypergraph by using one framework that uses indeed knowledge compilation. And it's in only 3 steps. So the first step is to encode the polynomials as CNF formulas that have some good properties that then you can exploit, okay? And immediately this encoding is not unique. So very briefly, the easiest way in which you would encode this, the structure of your polynomial, okay, for example, would be this one. But just very quickly, this encoding works out to preserve the truth property. But for example, it does not work out for the beta cyclicity. For that, you would need another one. So this is just to say that even the first step, one has to be a little careful about how you actually write down your CNF. But let's say that you write the CNF in a way that you have the properties that you want. And then using known results of knowledge compilation, you transform the CNF into a tractable representation C that can be something else. So for us, for example, in the proofs, we're going to use this special type of ordered binary decision diagram, but it can be also something else in general. And then once you have this tractable representation, you compute in polynomial time the value of this weighted Boolean function on it. So again, for us, for the OBDDs, how it works out is basically by doing dynamic programming in a bottom-up fashion, okay? Because we have this directed acyclic graph with a roof. You start from the leaves that have the value of the assignments, and you go on. So this is just to say, to sum up that in the end, we found one framework that allows us to show that there exists a strongly polynomial time algorithm to solve BPO, granted that your hypergraph is beta cyclic, which we already know, or has incidence treewidth of H that is bounded. And here already this is a generalization of what we knew before. But as I mentioned, the interesting thing is that we can also go beyond BPO. As in fact, we can deal with some extensions of it under the same structural assumption of the hypergraph. So basically, if H is beta cyclic or has a bounded incidence treewidth, we can also solve the following problems in polynomial time. We can add a special type of cardinality constraint to BPO. So basically here, we can add the requirement that the number of variables set to 1 at optimality must have some specific values, okay? So, and it works out for any as the subset of the cardinality of B. So very easily, you can see that you can encode the normal cardinality constraints like that, because you can add a lower bound and an upper bound on the sum. But you can also encode modulo constraints. So for example, you might want to ask that the sum of all the variables is even or is odd. And you can do it like that by specifying S correctly. But also other, of course, any modulo constraints that you might want, etc. So the second extension is instead subcase BPO. So basically here, we don't only want to find one optimal solution, but we want to find the K, or not the K, but K best optimal solution of BPO. And regarding this subK, as far as we know, there were no known results about tractability before. There were a few here, only dealing with the regular cardinality constraints and with a very restricted type of hypergraphs, but well, this contains all of them. And in step 2, we didn't know of any one before. And lastly, the last extension that we can deal with also is pseudo BPO. So basically, before, our monomials only were of the form product of variables. But now instead, we can also have something that we have some products of variables, but also products of the negation of the variable. And also you can mix and match. So you can solve in polynomial time top K pseudo BPO with extended cardinality constraints. Now that was from the theoretical point of view. But as I said, we can also use the more computational toolbox that is known for knowledge compilation. So all these compilers work basically the same. So we give them as input CNF, okay? And the compiler creates your other representation of the Boolean function. So we adapted one that is called default, that indeed it creates this special type of OBDD. And so you simply give it as input the CNF in the form that you want, okay? So depending if you want to encode, preserve the treewidth, so beta cyclicity or whatever. And then the compiler creates this OBDD. And at the root, at the end, it will return you the exact value of the weighted Boolean function, and you can adapt it to also get the optimal solution. Okay? So here we tested it on the usual dataset that is used for BPO. so the low autocorrelation binary sequences, also known as Bernasconi instances, and they can be found in poly for binary Philippe. And what we wanted to compare was the time in which we find the optimal value. So here we have the time that D4 takes, and then we compare it to skip, duplex, and Groby. We put a time limit of 1 hour. So whenever you see these dash, it's because they run out. And what we see is that basically for all the instances, the D4 compiler is much faster. And yeah, whenever we go into timeout, also the other ones that do. Oh yeah, and we tested it on also the other instances, but like for sake of state, I didn't put them. But also for the bigger instances, we see the same trend. So these instances have 2 parameters, number of nodes or of variables. And the second one instead deals with how dense your polynomial is. And actually it's related to the treewidth of the hypergraph. So we see that D4 actually works very well when the treewidth is small, but when it starts to be a little higher, it's not good. I mean, still better than the other ones, but the second parameter, the density, is really the bad one. And this is not very surprisingly because all these compilers work using stat oracles, and it's known that the stat solvers are very sensitive to this parameter of the treewidth. But in any case, so also from a practical point of view, it looks like we can leverage the existing toolbox from knowledge compilation and stuff. So this was everything that I wanted to tell you, and I managed to stay within the time, so perfect.
Grazie. Thank you. We have maybe time for one question, and otherwise we can take them in the breakout rooms after the next talk. Yes, Juan? Oh, I need to allow you to unmute.
Muted.
Give me 1 second.
Sorry,
no, you are allowed to unmute. Okay, good.
Okay, thank you so much for your presentation, Silvia. My only question is in the last data table that you are showing, you are yes, the results that you are showing for the standard MIP solvers. Sorry, because maybe I missed something in your talk. You are comparing the solution of the problem with the new solvers based on hypergraph versus some integer programming formulation of the same problem.
Yeah. So we
basically
gave the ILP.
But okay,
so,
because. Yes, it's not to be only want to know exactly we are comparing. No, in your experiment, you are implementing the same integer linear programming formulation of the problem. I understand that.
So to D4 we give the CNF.
The CNF
formula, and to skip duplex and Groby we give the ILP, where indeed we introduce one additional
yes, it's a
so we
standard.
introduced one variable for the one basically. So one variable for each monomial, and then we relax the equality constraint that define it. So we have YE less than or equal than XB. So basically, if XB is 0, then YE must be 0. And for the other way around, we use the sum of the XB minus YE is less than or equal than the cardinality of E. So the one that basically puts YE to 1 if all the other ones are 1.
Yes, well, but basically this problem can be very well formulated like an integral linear programming model using standard discrete expansion and the McCormick linearization.
Yeah, actually, they're exactly the McCormick one.
It's completely guided, and obviously in this chat, in this forum, everyone knows this result. But your result is very, very interesting because maybe this is the basic example of the kind of linearization that we usually implement to try to solve any nonlinear problem using discrete expansion. And sorry, about the time. My second question: have you tried to explore this method with a problem with full constraints? Not only because you are maximizing the pure binary function, but in this it's really very impressive, the speed up of the algorithms, but you don't have a real feasible a real polytop that
no, we don't have a polytop at all. No,
of
because we where is it here? We only use basically the stat solver, and they don't care at all about polytops, right? They only have these logical conditions. Their variables are always binary. They're just the assignment, and they only work with logic. So, and actually this like D4 compiler works for generalizations of WF, like it can be used for, in general, algebraic model counting, but it was first developed for like sharp sat. So counting the number of feasible assignments of a CNF.
Okay, thank you very much, Silvia.
So,
thank you for the organization.
Sorry, thank you,
Start.
Juan, for the question. We'll hope that you can continue the conversation in the breakout rooms if you're able to stay. If you're not, enjoy your evening, Juan.
Or you can send
Silvia,
an email.
thank you for your presentation. I'm going to stop the recording here.